Well, hi everyone. Thanks for coming back. In the last two lectures, I've been describing two different ways we can measure incidence in a population that's being followed over time. One was the cumulative incidence, which required that everyone be followed for a fixed period of time and there'd be no losses to follow up, no losses due to competing risks. And the other was incidence rate, which used as its denominator the amount of time a person was followed, and that can take into account the follow-up ending because a person's being lost or being no longer at risk because of a competing risk. Well, what's the mathematical relationship between the cumulative incidence and the incidence rate? You would expect them to have some relationship because both of them are measuring something in common, incidence rates. Both have the same numerator, they just have different denominators. Well, let me introduce this relationship with a question. So let's suppose you had 1,000 people and you were going to be following them for a year. And no one was being lost to follow up, no one was being lost to competing risks. Everyone was either going to develop an outcome, say it's death, or they were followed for a full year. And let's suppose you did this study and you observed that the incidence rate was 10 cases for every 100 person years of follow-up. Now, how much person time do you think you would have observed in this study when you followed 1,000 people for 1 year? Well, if no one's being developed in the outcome, then you would expect approximately 1,000 person years if I followed 1,000 people for 1 year. Now, we know that's not strictly true in this case because some people are going to develop the outcome. Some people are going to die before the year ends, and therefore they're going to contribute less than a full year of follow-up. But approximately, we might be able to say we would observe 1,000 person years of follow-up if we followed 1,000 people for a year. How many cases of disease, say death, would you expect out of these 1,000 person years of follow-up? Well, the incidence rate says for every 100 person years, you'd expect to see 10 cases. You've got 1,000 person years. You'd expect to see 10 times 10. You'd expect to see 100 cases of disease occurring out of those 1,000 people when they're being followed for that period of time. So finally, what would be your estimate, your best guess of the 1 year cumulative incidence? Remember, cumulative incidence is number of cases of disease, death, divided by number of people you started with. We started with 1,000 people, and we ended up with 100 people developing disease. We would expect 100 over 1,000, or 10%, to develop the outcome, to die during this 1 year follow-up. So those are the calculations just typed out. But the last one, that's 10%, notice numerically it's equal to the following calculation. Take the incidence rate, which is 10 cases for every 100 person years, and multiply it by the duration of the follow-up, which was 1 year. And if we do that, we get the same answer for the cumulative incidence. And that brings us up to an approximation formula for approximating the cumulative incidence if only you had the incidence rate. So if your data only allowed you to calculate incidence rates, you had losses to follow up, you had losses due to dying from other causes, if you're looking at developing CHD as your outcome, you can measure incidence rates, but as I say, you can't measure cumulative incidence directly. A way to approximate what the cumulative incidence would be from the incidence rate is using this formula. Take the incidence rate and multiply it by the length of the follow-up, the time period of follow-up. And that'll be an estimate for the incidence, the cumulative incidence, corresponding to that incidence rate being applied to that period of time. And since the cumulative incidence can also be described as an estimated risk, often we see this described, this formula says that the risk is approximately equal to the incidence rate times the duration of the study. So for example, as we had in the previous case, if your incidence rate was 10 cases for every 100 person years, and you were following people for 1 year, the 1 year cumulative incidence, or the 1 year risk, would be that incidence rate, 10 per 100 person years, multiplied by 1 year, and we get that value 10% that we had when we figured it out by hand in the previous slide. But there's a problem with this formula. And it's a problem we talked about before with populations A, B, and C, is that whenever we follow people over time, once you develop the outcome, you're no longer at risk for developing it again. So your population at risk might be a certain number of people, in this case 1,000 people at the beginning of the study, but not all 1,000 people are going to give you a full year of follow-up. We estimate about 100 of these guys are going to die if death is our outcome. So we're not going to get a full 1,000 person years of follow-up. And that's what this formula essentially is assuming. So this formula works very well when the population, when the incidence rate's very small. So very few people get the disease, therefore almost everybody gives me a full period of follow-up. Or when the follow-up period is very short, again, not enough cases of disease would happen. So the problem with the formula is that it doesn't take into account the correct amount of person time. The fact that these cases the number of cases don't contribute a full person time of interval as the non-cases do. So the approximation works very well when the incidence rate is small or when the duration is small. And to see that, let's think about population C again. Remember, population C was a population which had roughly a constant incidence rate. Incidence rate was about 0.1 cases for every 1 person year of follow-up, or 10 cases for every 100 years of follow-up. In this case was assumed to be a constant value. If we use that formula with this incidence rate to estimate risks, what will we end up with? Well, if I want to know the 1-year risk of getting a disease, death in that previous example, I take the incidence rate, which is 0.1 case for every 1 year is the same as 1 case for every 10 years. I take the incidence rate, 1 per 10 person years, multiply it by 1 year, I'd get a risk of 10%. If I want a 4-year risk or 4-year cumulative incidence, I take the same incidence rate, but now multiply it by 4 years, and I get 0.4. Okay. If I want a 10-year risk, I take that incidence rate and multiply it by 10 years. I get a value of 1 for the 10-year risk. If I want a 12-year risk, I take the incidence rate, multiply it by 12 years, and I get a risk of 1.2. Well, wait a minute. Marcello's told me that risks, probability, cannot be any bigger than 1, and they can't be any smaller than 0. So suddenly this formula is giving me estimated risks that are mathematically not possible. They're bigger than 1.0. And the problem is I'm using this formula in a situation where it doesn't apply. It works very well when the incidence rate is small and the time period of follow-up is small. But now I'm talking about a long period of follow-up, 12 years. And the problem is the longer I follow people, the more cases of disease will occur, the fewer amount of person time those cases of disease will be able to contribute to my total population. So I'll no longer get 1,000 person years of observation for following 1,000 people for 12 years. During that 12 years of follow-up, many people are going to die. And those people who die do not contribute a full 12 years of follow-up. So I need a better formula. A formula that takes into account that the population at risk is shrinking over time as you follow people longer and longer. And we get such a formula from survival analysis, something else that Marcello will be talking about towards the end of this course. That's why we epidemiologists need people like Marcello, need statisticians to work with. So some advice to give to everybody. If you want to start a career in epidemiology, make a good working arrangement with a statistician to help you figure out some of these calculations. Or you can do what I did and marry a statistician and think of all the free consulting time you can get over dinner tables and things like that. But that's a topic for another day. But what's the better formula to use? Well, from population C, we saw that the 4-year cumulative incidence was 34 cases out of 100 people was 34%. The previous slide, using that approximation formula, said the 4-year cumulative incidence would be 40%, which is too high than the 34%. So it's breaking down. It's breaking down because it doesn't account for the diminishing population at risk that happens over time. What's a better formula to use? Well, here it is in gory detail. This formula comes from survival analysis. It says the person's risk is equal to 1 minus the exponential function of minus some integral of incidence rate measured over time. Calculus is suddenly starting to to relive in your memories if you took a course in calculus. You can simplify this by making an assumption. If the special case of a constant incidence rate function is true, in other words, if the incidence rate functions flat over time, and that one single value, total number of cases divided by total amount of person time, holds for the entire period of follow-up, this semi-complex formula up top simplifies to say a risk is equal to 1 minus e, the exponential value, exponential function, of the negative incidence rate times time period. So what's in this numerator, in this exponent here, again is incidence rate times time period. Multiplied by -1, that's the negative sign, and we're taking e to that number. E is taking into account, if you want, the exponential decay in the population at risk that's being followed over time. Fewer people are being at risk at later points in follow-up when we follow a group of people over time. So if we go back to population C and take that constant incidence rate of 0.1 cases for every 1 year of follow-up, multiply it by 4 to get the 4-year cumulative incidence, as we do over here. But don't just go with that value, take the negative of it, take e to that value, subtract it from 1, we get a value of 0.343, which is very similar to the value of 0.34 that we saw if we directly measured cumulative incidence. So to estimate cumulative incidence, to estimate risks from incidence rate data, we typically use this special case formula to say that a risk for a certain time period is equal to 1 minus e to the negative the incidence rate times the time period. That's the mathematical relationship between incidence rate and cumulative incidence. Okay, so I'm going to stop here, and when we come back next time, I'll talk about the relationship between incidence and prevalence, another mathematical relationship that turns out to be a little bit simpler to derive than the one we just talked about. It doesn't require knowledge of calculus. If anything, it requires a little bit of knowledge of physics. So see you guys next time.